matrices. And I would like to maybe keep that theme maybe for the rest of the quarter and talk a little bit more about numerical things, maybe for the next 3 weeks. So let's start with a few simple examples of divide and conquer, sort of understand the paradigm of divide and conquer. So, remember I said that in dynamic programming, coming up with the recurrence is hard, but then the proof is sort of easy. Because once you have the recurrence, the proof is almost evident. With greedy algorithms, coming up with the algorithm is easy, but then the analysis is a lot harder. And sort of in divide and conquer, unfortunately, it's the worst of both, right? Sometimes coming up with the algorithm is challenging, and the analysis is also can be challenging. So how divide and conquer generally works is it's a way of, I like to think of it as a way of using recursion to solve problems. So generally the way that you think about divide and conquer is you say, break up the problem into sub-problems. So this is the divide step. Solve each sub-problem recursively. So I think of these, many students, and indeed like when anyone sees this for the first time, they think there's something circular in this reasoning. How can you solve a sub-problem recursively when you don't even know how to solve the problem? Like somehow it seems absurd that one can even use this. And then what you have is the conquer step, which is combine solutions of subproblems into a full solution. And this is the conquer step. So it turns out that all the work is really being done here. Because here it seems like you're not saying anything specific to the problem itself. You're just dividing. But when you combine solutions and subproblems, that's when the actual work happens. So another way of thinking about this is the divide and conquer, divide and conquer principle basically is the following. So let me zoom out a bit. Okay. The divide and conquer principle is if there is an algorithm to combine solutions of subproblems into a full solution, then there is an algorithm to solve the full problem. So the way to think of this is, instead of trying to solve the full problem, if you can simply come up with a way of combining solutions, then the divide and conquer principle says there's like an automatic formula to solve the problem. So this gives you an easier way to start approaching a difficult problem. So instead of trying to solve, you say, okay, suppose I could just get solutions to subproblems And if I just know how to combine them, then divide and conquer says, well, there is a generic way in which you can do this. The running time, which is the runtime analysis, which is often the most challenging part, the running time analysis, so this basically will be done through a recurrence of the running time. So this is often the tricky part, which is getting the runtime analysis. Okay? So unlike dynamic programming or unlike greedy algorithms, or at least the ones we have seen thus far, the running time analysis was not particularly hard. For dynamic programming, it's quite obvious. It's usually just some kind of nested for loop, because it's some table, you're filling up a table, each entry you say how much time does it take, so on and so forth. In greedy also, like the algorithm by itself in the end was not that, the running time is not difficult to analyze. The correctness is hard. Here the running time is going to be, it requires some little bit more math to do. Okay, so before, the best way to do this is to give you an example of a simple divide and conquer algorithm, and the classic example is Mergesort. So how many of you have seen Mergesort before? Okay, so I suppose most of you have seen Mergesort. Do you want me to do the analysis again? I don't know. I can recap Mergesort if you think there is some utility for that. Raise your hand if you want to see me just do Mergesort again. I'll do it quickly. Yeah? Okay, so all right. So let's go ahead and do Mergesort. Okay, so what is our problem? The most classic of CS problems, sorting n numbers that are in an array. And you want to sort n problems. So what is the merge sort idea? It says let's do divide and conquer. So here's your array. I'm going to refer to this array as A. It says, suppose you already, so let's call this part L and this part R. Suppose we sort L and R recursively. We need a combine, or what is called a merge algorithm. And once you have a merge algorithm, you can do merge sort. Okay, so let's. Okay. All right, so let's talk a little bit about merge. So what is the merge step? Merge says given to sorted, given to sorted arrays, output the sorted order of the union. Right? That's what merging is. So it says if you have two sorted arrays, I'm just going to refer to these as A and B here. And A and B are sorted. And you want to basically combine them to get C, which is the sort of A union B. It's an abuse of notation, but hopefully you understand what I mean, right? Basically, put all the elements together. And so hopefully you recall that this can be done in linear time. Right? How do you do this? You keep one pointer here and one pointer here. You compare these two elements. The smaller element goes here, and then you move that pointer to the next, and then you keep comparing, and then the smaller element goes in here, so on and so forth. Right? Is this clear? Right? This is how you merge sorted arrays. This is sort of a classic thing that you see in a basic, like a data structures course. Right? One of the first things you see, or not first things, but one of the basic things that you see in an undergraduate algorithms course. And so what we know is that merging sorted arrays can be done in linear time. Right, so if the length of this is n and the length of this is m, basically you need O of n plus n operations or time or whatever, right? Okay, so everybody remember this? This is how you sort. This is how you merge sorted arrays. I haven't given you the code, but again, you can go and look this up. It's just basically you have two pointers that march through the arrays. Okay. So now that you have a merge procedure, how are you going to do merge sort? So what I'm going to give you here is sort of the paradigm of divide and conquer in action. Okay, that's the way to think about it. So let's do merge sort of an array A. I'm going to be a little casual and maybe sloppy with my variables and types and things like that, because that's not my aim, right? My aim is not to focus on the programming, sort of the language part of it, but rather the basic principles. So we'll say, okay, so if the length of A is 1, then you just output A, right? This is the base case. Okay. Otherwise, we'll say that L is A going up to n over 2, floor, ceiling, whatever way of rounding it is, and R is equal to A going from n over 2 plus 1 to n minus 1, so everything else, right? So here is my array. I split in the middle. I have L and R. Now I call merge sort of A. Actually, okay, so it's outputting something, right? So maybe I'll say that, sorry, let me try to write, my apologies. I'll say L sort, I'll put a subscript, L sort is equal to the merge sort of L. R sorted is the merge sort of R, and then you output merge LS RS. Right? Okay, any questions about this? Please ask me so that I can clarify, because now I want to talk about the analysis and then sort of dig even deeper into this. So there's my phone. Oh, there it is. Okay. Yes. Questions? All good? Okay. So this is merge sort. So, you can kind of prove that it works basically by induction, right? Because if merge sort inductively works and merge works, then merge sort is going to work. So this is the general paradigm for divide and conquer, right? Which is up to step 5, there is really no reference to sorting explicitly. There's really nothing about sorting that you're doing. You're just dividing the input and then calling some procedure recursively. Instead of merge sort, it could have been something else. When the input is small enough, then you just have some simple algorithm to solve it. Just do it directly. The base case is usually trivial. So up to step 5 is just the divide and conquer paradigm. And in step 6 is really where the work happens. This is often, maybe this is clear to you because you've seen merge sort, but this is worth reminding oneself that all the work is happening in the merge operations. The rest of it is simply, in some sense, just like scaffolding. And any divide and conquer algorithm looks a lot like this up to step 5. I'll give you another example and you'll see that it works similar to that. All right? So the challenging aspect here is to work out the running time. Because there's no for loop, there's no loop that you can count. So how do you work out the runtime? So for the running time, what you have to say is let T of n be the worst case, running time of Mergesort. Let me zoom out a bit. Of Mergesort on input of length n. Let's write down the running times of each of these steps. So step 1, that's easy, that's just O of 1. Step 2, okay, it depends on which language you're in. If you're copying things, it's O of n, but if you could just take pointers, then it's O of 1. Right, I'm just going to assume, suppose you can just use pointers. Right, so both of these are going to be O of 1. Right? So Mergesort of L, so how long does this take? Yeah? T of n over 2, right? Because the array is split in half. So that is T of n over 2. The next one is T of n over 2. And the last one is O of n. Right? So if you sum all of these up, that gives you the runtime of the whole thing. So this is an upper bound, right? Because this is saying this is the worst possible. So what you get is that T of n is less than 2 times T of n over 2 plus O of n. And usually you need a base case as well. T of 1 is just O of 1. You could even put an equal to sign there because technically O is an upper bound. But I'm writing this in this way because this is probably more familiar. Okay, so this is the base case. And this is the recurrence. Okay. So just give me a second. Okay, so is this clear? Okay. How do you solve recurrences? It's okay. So let's. So the question then becomes, how to solve recurrences. So approach 1 is, I mean, you might think this is funny, but find a theorem that solves it. And indeed, there are theorems that you can pull up a theorem from somewhere that solves it, which is actually what many students will do, right? So you go and look up CLRS, and there's something called the master theorem for recurrences. You plug that in, and you get some solution, which is fine, except the annoying thing is sometimes you get a recurrence which is in a slightly different form. It has some modification. You're not sure. So it's useful to understand a more, let's say, a way of solving it by yourself, but one that doesn't involve too much effort. So the second approach, which is what I want to tell you, is guess the solution and verify by induction. this is the actual proof. But this is really where you have to kind of figure out how do you guess. So you could say, how do I guess the solution? So I have something distracting me. Okay. So the way you do it is really, and this process is what I want to show you, and there is some sort of method to how one does this. And you'll see that it's flexible enough that every recurrence that we come up with, you'll be able to sort of solve through this. So you guess by basically, I'll say, writing down the recursion tree and tracking the merge, which is basically the combine work level by level. Okay, this is the general principle. So we're going to basically do this. Okay, so what do I mean? So I'm going to write down the recursion tree of Mergesort. I'm going to write down a few things. So this is a recursive call. I'm going to put a number in here. This is the input size. Okay? So this has 2 children. What is the input size in each of these? N over 2. N over 4. So on and so forth. Now, let's go back to our procedure here. Let's go back to our procedure, and let's observe that if you go to the recursion tree is sort of handling the work, the running time of these calls. But steps 1, 2, 3, and 6 are sort of associated with that call. So steps 1, 2, 3, and 6, 1, 2, 3, and 6 is the work done in that call. Does that make sense? So in that call, this is the work done. Everything else is sort of associated with a recursive procedure. Okay? Questions? All right. So what I'm going to do next to this is to write an upper bound on the work. So how much work was done here? You say it's O of n. Right? So I can instead write this as, so T of n is at most 2 of Tn over 2 plus C times n, where C is some constant. It's some fixed constant. Right? That's what this O of n means. O of n means it's some constant times n. Yes? Okay, so how much work is done in this? At most C of n. How much work, extra work is done in this call? At most C of n over 2. This is at most C of n over 2. And this is at most C of n over 4. So on and so forth. What you want to do is really sum up all the work. You want the sum of all the work. Right? That's what you want. Instead of trying to sum it up in some other order, sum level by level. That's the idea. This works in general for any kind of recurrence that, well, not any, but most recurrences that you will see in this course are probably you will encounter in your life unless you become a theoretical computer scientist and work on complicated things. Most recurrences that you will see can just be, you just do level by level, you'll see a pattern. So the sum at this level, so I'm now going to basically sum at the level, well, this is at most Cn. If I add these two, I get at most Cn. If I add 4 of these, I get at most Cn. And how many levels do I have? I have log n levels, right? Because in the ith level, it's n divided by 2 to the I. So at log n levels, the total depth of this tree is essentially log base 2 of n. And in each level, I got C of n work. So the total work is at most Cn log base 2n. This is not a proof, right? This is just some sort of calculations, but this is almost a proof. I mean, if you really went through the effort, you could make this formal into a proof, but that's not what I would like to do. You can formalize this, then you would do some induction, you would do a bunch of things. But what you do is you can use this process to guess the solution. Indeed, if I gave you this recurrence, T of n is at most T of n over 3 plus T of 2n over 3 plus C of n. What about this recurrence? This looks very different. But indeed, if you apply this logic, you'll see the same pattern emerge. Any kind of split by a constant, n over 4, 3n over 4, will also end up giving you n log n. The issue, of course, is sometimes if you use the master theorem, I guess sometimes it gives you bounds of this kind, sometimes it might, depending on which version, right? What if it was like T of 2n over 3 plus 2n over 3 plus n over 4? What do you do then? But if you draw this, you could basically, again, just follow this level by level. What you see in this case is in all the levels, it's the same. You get the same bound. So you get whatever it is times the number of levels. Usually you end up in only one of 3 situations. They're all the same. It's an increasing geometric progression or a decreasing geometric progression. But regardless, it's easy to compute the sum. If it's a decreasing geometric progression, it depends on the first one. If it's an increasing geometric progression, depends on the last one. Otherwise, it's the number of things times times the depth, which is log n. Okay, my point is, if you draw this picture, whenever you have a recurrence, you'll get some idea of what the solution should be. But then you have to go and verify that this is correct by induction. And in that, there's a little bit of a trick. Okay, but anyway, any questions thus far? It's clear? How many of you have already seen this before? It's fine if you've seen it before. It's good. Yeah? There's like a half hand up. So like you saw half of it but not the full thing, or you saw it but you don't really remember it. Okay. It's like lodged somewhere in your brain somewhere. Okay. Good. Let me just check the chat for a second. See. Okay, good. How do we verify this is correct? So say, okay, let's do it by induction. Okay, now what I'm going to do is I'm going to give you a wrong proof by induction. And you're going to have to tell me where the error is. Okay? Okay, so T of n is at most 2 T of n over 2 plus C times n, and T of 1 is at most C. Okay, so why did I put the same constant? I mean, this is a big O, right? So this is some constant, and this is also some other constant. I can just upper bound by whatever is the largest constant. I just put the larger constant amongst both of them. Yeah? Right? So that's fine. So it's just convenient. Instead of doing C and C prime, it's not going to make much of a difference. Okay, so this is your recurrence. Okay, so I'll say wrong theorem. I'm going to prove to you now that T of n is O of n. Okay? What's the proof? Okay, so proof by induction. Proof by induction. Now watch carefully, there's a mistake somewhere. Okay? So I'm going to prove what by induction? I'm going to prove that T of n is O of n by induction. Okay? So base case is what? T of n is at most C. We know this. And this is at most O of 1. Okay, so base case is fine. The induction. So by the induction hypothesis, T of n over 2 is O of n over 2. So T of n over 2 is at most d times n over 2 for some constant d, right? That's what this means. Okay, so now that means we know that T of n is at most 2 times T of n over 2 plus C times n, which is at most 2 times d of n over 2. I just plug this bound in, plus Cn, which is at most d plus C times n. So then okay, stare at this carefully. There's your proof. I just proved that Mergesort runs in O of n. I have invalidated most of your education that you've received thus far, right? What you've been taught is wrong. I just proved to you that Mergesort runs in linear time. You know you think you know where the error is.
Are we allowed to do like O of n over 2? Isn't it just also like O of n?
Sure, it's also just O of n. I mean, but that's not the error, right? I mean, essentially T of n is at most this, right? That's what this says. Huh?
You're jumping from n over 2 to n.
The induction variable.
So, for example, the inductive case you assume is like instead I, and you're jumping from I to I plus 1.
No, you can, but okay, strong induction, right? You can do strong induction. Use strong induction, so you assume it true for everything up to n minus 1. I mean, if this bothers you, you can do strong. Strong induction means that you're assuming it true for every n up to n minus 1. Every argument up to n minus 1.
But that doesn't work for every n. You need to have an n to the power of some integer.
Which doesn't work? You mean, oh, because n over 2 is not an integer?
Yeah.
Assume n is a power of 2, if that bothers you. There's still an error, even if n is, okay, so suppose n is a power of 2. Let's say I prove this only for n of the form 2 to the I. Then that's not a problem. Okay, so forget my class. We can just discuss what is wrong with this for the rest of the lecture, because this is important. Yeah?
It feels like you're only considering the linear portion of the theorem, but not the recurrence part.
No, the recurrence is done right here, right?
Okay. Like, but T of n over 2 is Like you have to recur on that.
Yeah, but that's the induction hypothesis,
Okay.
right? That's the induction hypothesis, so I plug that in.
Right.
Which is legit, right? I mean, I assume, I want to prove I want to prove T of n is O of n, is linear.
Okay.
So I say, well, okay, it's all linear on half of the thing. So where's the catch?
What about the D?
What about the?
It says there's for some constant for the D,
Yeah.
but there's some constant for the C.
So the C is a constant that comes from your recurrence. Okay, and the D is the constant that's coming from the induction hypothesis. Okay, you're warming, you're getting warm. There's something, maybe there's something there, maybe there isn't, I don't know. But I bet you haven't seen this thing before. Even if you've seen, you've probably seen the proof that it's n log n. You learn a lot more from wrong proofs than by right proofs. Because the right proof is like, yeah, okay, yeah, I see that, I see that. But there's something here that's going on. What does it mean to be O of n? What is the definition of T of n is equal to O of n? What does that mean?
The highest order is less than n to the power of 1. The highest order of the
Okay, but be more precise.
So it seems weird. You have O of n divided by 2.
So O of n over 2 bothers you.
Yeah.
But then this shouldn't bother you, right? That's basically what it's saying. This is just saying the order. You said linear, so order, you're right. So O of n means the order is linear, right? So it's n over 2. And it does seem correct. So we can sort in linear time. Let's move on now. What does T of n equals O of n mean? If you get to what it really means, you'll see the error. What does T of n equals O of n mean, formally?
You can have constant, additional constant term.
You can have additional constant term, but does someone know what is like a formal statement of T of n is equal to O of n? Like what is that? There's some long definition. There's like this definition with two constants, like there's the n0 and this and that. What is that?
When n is big enough, like
Okay.
for every n, like
Yes. Okay, good.
less than some constant times n.
Okay, so say that again. So it means that, so let's just say T of n is equal to O of n. Equivalent. That means for all n greater than n0. Yes?
Like the number of operations is less than c times n.
Okay, so
C times n.
let's not use c because we use c for this. Let's use a different constant. Let me call it c prime. Right, good. Now do you see the problem? Over here, you have to fix c prime, and it has to hold for all n. So you fix the constant, works for everybody. Here, I cheated. I started with a constant d. I end up with a constant d plus c. Initially, so this is fine. This is actually not a problem. I started with a constant d, and I ended up with a constant d plus c, which means it's not a constant. If it's changing with n, it's not a constant. What this means is, think of it, the game as follows, right? When you say T of n is O of n, Your proof has to choose a constant at the beginning of the proof and say, I'm going to upper bound by this constant. And then you inductively assume that constant, but you have to get back the same constant. Because if you change the constant, it's not constant any longer. Does that make sense? It's a subtle bug. Which is why, whenever there's confusion, go back to the original definition, this is a common error when you say, oh, O of n plus O of n is O of n. That's correct, but you have to be careful when you do that kind of a step.
Are we upper bounding by like d in the induction?
So what you should do in the induction is if the inductive hypothesis is d, you have to get d times n over here to complete the induction. But you're not going to get d times n, you get d plus c times n. So actually this is not true. You're not going to be able to do this, which is why you'll actually need the n log n. Yeah, sort of, kind of, right? So, like the O notation is, it's very powerful, it's very useful, but it's also very easy to make errors in formal proofs when you use the O notation, because you think, oh, O of n is a constant times n. What you're not keeping track of is it has to be the same constant for all n. Whereas here, I changed the constant from n over 2 to n. I change it from d to d plus c. So it looks like it's linear here, and it looks like it's linear here. But I can't give a different, it's like, I'm saying, oh, it's a line here and it's a line there, but that means they have to have the same slope at both places. If they don't have the same slope, then it's not a line anymore, right? So it's sort of the same idea. All right? Yeah, go ahead.
So basically, at each recursive step, there's like a different constant for each recurrence line.
Right, so which means that it's actually not O of n then.
Yeah, it becomes like greater than O of n because of all the different constants, I guess.
Instead, it's not following the rules of O and n, of O of n, because O of n says you have to choose a constant that works for all n. And when you try to do that in the induction, it's forcing you to choose a bigger and bigger constant as you go up the recursion tree. Which means that, so the problem is, so you might say, okay, let me choose a bigger constant. But when I choose a bigger d, d plus c is still bigger. So no matter how I choose the constant, I cannot escape this problem. In some sense, that's why d has to depend on n. It turns out the right dependence is log n. That's one way in which you can incorporate everything. That's sort of another way of looking at it. The fact that the d is increasing tells you, oh, d should actually be a function of n. In which case, it's not linear, but it's something else. And that something else will be n log n. Okay, so let's try to do another proof. Okay, so now that we have this, let's try to argue that t of n is O of log base 2. And of course, it doesn't matter what base I use, but the reason I want to write the base is so that I don't wrap myself into any errors with a constant any longer. Okay, so now let's do the proof. So the first step is I choose the constant. Okay? So let us prove that for all n, t of n is at most c times, I'll put a c prime here. It's a different constant than the original. Right? I will choose c prime later. So you sort of have to watch what I do and then you'll see. So what is the base case? The base case is t of 1 is at most c, right? So technically it looks like I have a bit of a problem here, because when I put n is equal to 1, I get 0. It's not going to work. So you want to say something or no? Let me, this is a minor hitch, so let me do something. Okay, so let me just say when it's 2, you can sort A and output. Let me just say the base case is 2. Let's just assume it's a power of, because there's something else I want to show you. I don't want you to get caught up in the base case. Okay? I don't want you to get caught up in the base case. So in that case, T of 2 is at most C, right? And this is clearly the case over here, because this is at most C prime 2 log base 2 when C prime is greater than C. So I can just choose C prime to be greater than C. So you kind of have to go through the proof to figure out what the choice is, but you can choose it. Okay? Now let's do the induction. So T of n is at most plus C times n. Okay? By, if you prefer, the strong induction, T of n over 2 is at most C prime n over 2 log base 2 of n over 2, which is equal to C prime, okay, let me do this carefully, n over 2 log base 2 of n minus 1, right? I'm just splitting up the logs, right? Okay, which is C prime n log n minus C prime n over 2. Okay? So now I'm going to plug this bound into that. So I'll say T of n is at most 2 times C prime n log base 2n divided by 2 minus C prime n divided by 2 plus Cn. I'll get C prime n log base 2n minus C prime n plus Cn. C prime, just choose C prime to be anything greater than C. This is at most C prime n log base 2n, completing the induction. Okay? Is that clear? Questions? It's very easy. I mean, even I can make errors when writing such proofs, right? So you have to be very careful that you're not doing something with big O. So typically when you have a proof with big O, you always try to convert the big O into whatever, fix a constant at the beginning of your proof, and then make sure you get back the same constant. Note that here, it's almost magical that the C of n that's being added needs to get cancelled out, and there's this minus thing that cancels it out. There's a minus C prime n that I get because the n over log base 2 of n over 2 is log base 2 of n minus 1. That minus 1 gives me what I need to cancel things out. So it's a good time for me to pause. So stretch your legs, take a breather. We'll take a break for a few minutes. And then when we continue, I'll give you another example of divide and conquer. Any questions in the chat? Go ahead. We'll take a break for a few minutes.
If this proof had C prime extended by some other constant value, then that would be wrong. Then.
Say that again. Yeah, exactly. So the thing is, you get back the C prime that you started off with.
Exactly.
That's important. Exactly. That is precisely the point, right? I started with a C prime over there, and then I get back the same C prime at the end. Whereas in the previous proof, I started with, I guess I called it D, and then I ended up with D plus C. That is incorrect.
Just a quick question. So what about the like big omega or big theta for the down the big O? I mean,
If you wanted an omega bound,
things like
yeah, then you would have to get a lower bound for these things. That then becomes a little trickier because technically T of n was defined to be the worst case running time. You would have to change things over here. Yeah, you would have to say that this is at least the worst case. And yeah, so
I mean for the constant for the if the proof for the constant.
the constant will go through pretty much as is. Like the same arguments will go through. I mean, you would have to change the constants over here. So if you then, you would say C prime needs to be less than C so that you can get the opposite. Because if C prime is more than C, then you get the upper bound. When C prime is less than C, you get a lower bound. Which makes sense, right? That you're upper bounding by some constant, lower bounding by something else. So you have to obviously choose something else. But this analysis will go through as is, but you have to be a little bit more careful in getting the recurrence. Because it's not obvious that you can just flip this, because this is the worst case, but what if it ended up being something where this was better than the worst case? Then the lower bound, but if you have to be a little bit more careful, you just track the amount of work. You say, look, you have to do a merge step at each node of the recursion tree. The merge step is theta. So just sum up the work done in the merge steps, and that gives you the omega bound. Does that make sense? Yeah. Yeah, I'll keep this here. Again, we'll give you a few minutes to breathe. All right, let's continue. So now that we have this recurrence in front of us and this theorem, this is something that henceforth we will just invoke whenever we see such a situation. So what is such a situation? It means divide and conquer, where you have two problems of half the size, and linear time combined is n log n. Because this recurrence is probably one of the most important. Like, this is the one that appears over and over again. So I want to describe another problem where you get the same recurrence. And then I want to describe another recurrence that also appears and comes up quite a bit, but not this one. So this is sort of the classic n log n. And again, like, just to step back, ignoring the subtleties of that proof, if there's something that you really need to understand, it's this picture. Right, this is the picture that I really want you to get. Because, not everybody writes proofs, but divide and conquer is something that does come up every now and then. And even if you can't figure out the proof, it's useful to have some understanding of just this tree and how this works. Even if you don't have to build the tree every time, just to know that this is where the n log n comes from. Okay? So let's look at another problem. And this is a The only problem with writing with the fountain pen is that it's sensitive to the paper that you write on. And there was a paper, that paper has been face up in my office for about 1.5 years. So there's a layer of dust on it and it doesn't write well on it. So anyway. Okay, so let's look at another problem, which this is given in CLRS. It's a nice problem, and this is, it's called the stock market problem. So the input is an array A of prices of 1 unit of a stock, or any goods that you want. So here's your array A. You can interpret this as like your ticker. So it's telling you what the price of a stock is. And we buy 1 unit of stock on day I and sell on a day j greater than I. So it's important that you sell after you buy. You might think that's absurd, but of course, these days you can sell before you buy. This is called shorting a stock. But you're not allowed to short stock in this problem. Okay? So you buy 1 unit of stock on day I, and you sell on day j. The profit is A of j minus A of I. Right? This is the profit that you make. And so the problem is to compute the maximum profit, which is just equivalent to saying maximize over all j greater than I, aj minus a. This is the problem, right? You have an array and you have to compute this. What if you could short stocks? Then what do you do? Then how do you compute the max profit? Yeah?
You just reverse it. It'd be A I minus AJ.
Sure, but give me an algorithm, linear time algorithm, that computes the maximum profit if you could short stock.
Take the min and the max.
Take the min and the max, right? Look at the max, that's take the min. And it's the max minus the min. Because it doesn't matter which is before which. It's the constraint that j is greater than I that makes it challenging. So if you can short stock, then what you'd obviously do is you buy on the day it's the cheapest, and you sell on the day it's the most expensive, and you can sell before you can buy. So, okay? But so in this case, we're not shorting stock. So ignoring the stocks for now, suppose you just want to compute this. How many of you have seen this problem before? Kind of? Okay, so some of you have seen this problem. Okay. Do you remember the running time for this algorithm? Yeah?
Do this in linear time.
You could do it in linear time.
Like with 2 pointers.
With?
With 2 pointers.
It's not that obvious to do it with 2 pointers, though. Huh?
And
You can do it in nlog. Actually, 2 pointers, you can, but it's a little tricky.
If I understand correctly, you
Yeah.
can only buy and sell once.
Only once, right?
Right, right. I think you can do it in linear time with 2 pointers. You have to keep updating the pointers. It is tricky. There's a trick to it. But I do remember you could do it.
You can. It's not that obvious to do it with 2 pointers, but you can. I mean,
Like the first pointer, like you keep track of the lowest you've seen so far, I guess.
you basically what you observe is it's kind of you're basically using some kind of a stack. Actually, what you're saying is if the price at a point dropped, then instead of buying here, you should have bought there.
Yeah.
So you can keep track of that. The problem is when things increase, then you don't know. Then it may have been better to buy there. Yeah?
That's why you can keep track of a running profit. So if you found that you got a greater profit, you just update the profit.
Right. So, but you have to be careful because the profit at a particular point depends on the maximum in everything seen so far.
Right.
So what if, okay, so like what you do is you kind of go backwards, right? You say that what is the maximum up to a point? And if you can keep track of the maximum up to that point, then you know the profit on buying on that day. And then you kind of have to keep track of this. Anyway, so it's not, one can do it, it's not obvious. But let me tell you how to do it with divide and conquer. Because then actually, in some sense, if you follow divide and conquer, it becomes pretty obvious how to do it. So if you do divide and conquer, you say, well, okay, suppose I have the max profit here. Max profit, which is buy and sell in less than n over 2. And suppose you get the max profit here, which is buy and sell both greater than n over 2. So which case is left? Buy in the left and sell in the right. But that's easy to find out what the max profit is. Buy in the cheapest in the left and sell in the most expensive on the right. Right? So if you get recursively the solution in the left half and you get the solution in the right half, the combined step is easy. Does that make sense? So I'm just saying you can get the max profit here. The case left, so the case left is buy less than n over 2 and sell greater than n over 2. So here the profit will be, or the best profit over here is the max over all j greater than n over 2 of aj minus the min over all I less than n over 2 of ai. This is your profit. So this would be the combined case. I'll write out the pseudocode shortly. But clearly you can compute this in linear time. And you'll basically see the Mergesort recurrence all over again. Right? Because T of n is 2T of n over 2 plus linear time, and then you just compare all three and you output. So I'll put this down. Any questions about this? Yeah.
In constant time?
I'm sorry?
Can you do it in constant time? The third case.
How?
If you pass the max and then recursively.
Good. Yes, you're right. You can do it. So we'll come to that. Good. So that would be the next thing. Yes. If you pass the max and min recursively, you can do the combined step in O of 1, and you'll get another recurrence that I wanted to talk about. Okay, so any questions about this? Shall we continue? All right, so I will write out the pseudocode for this so that so that we have it, and then we can work with it. So I'll just say this process max profit of A. So for the base case, I'll just say like if the length of A is, I don't know, less than or equal to even 2, then just solve and output. Right, then it's easy, right? You just look at the difference. It's fine. Okay. Otherwise, what I'll say is that the left profit is equal to the max profit of A from 0 to n over 2. The right profit is the max profit of A going from n over 2 plus 1 to n minus 1. Then, let's say compute what I'll just say compute, for lack of a better word, I will just call this the third case equal to, okay, so maybe I'll say compute the best cell, which is the max of j greater than n over 2 of aj. Compute best by min I less than or equal to n over 2 of ai, and output the max of the left profit, the right profit, and the best by minus the best cell.
Is it cell minus spot?
Correct, sorry, of course. Cell minus the by. So. Right? And so for running times, we get O of 1 here. This is T of n over 2, T of n over 2, O of n, O of n, O of 1. And so we get our friend T of n is at most 2 times T of n over 2 plus O of 1. T of 1 is O of 1. And so T of n is O of n log n. Right? So while admittedly there are these two-pointer solutions, this is sort of a lot easier to come up with just as an idea. Right? So you can just use divide and conquer straight off the bat and get n log n. The trivial algorithm, of course, is n squared, right? Just do all pairs. Okay, good. Okay, now there's a clever idea to do the combine and O of 1. So do you want to repeat what you had suggested?
For every call of max profit, you also pass the max and min of that sequence. So you generate the new max and min, you just take the max of the two max from left and right, and similar to max you can do it min.
Exactly. So I don't know if everyone understood. It's a very clever solution. The idea is, okay, so why are you getting O of n? Because you have to compute the max in the right and the min in the left. But suppose the recursive procedure would output the min and the max. So the recursive procedure outputs not just the profit, but it outputs the min and the max. Now, you have to do more because the combine step also has to compute the min and the max to send. But that's easy, right? If you have the min on the left and the min on the right, the total min is just the min of those two. The max on the left and the right, that's just the max of those two. So I'll write the pseudocode down. But this is a very clever operation to do to reduce that O of n to O of 1. And then we have to see what that happens to the recurrence. The recurrence now is actually that's going to be linear time then. That'll give us a linear time algorithm. So the idea is that the procedure returns a tuple, which returns the profit, the max, and the min. It's going to return three things. Okay? So let me rewrite this. So now you have the max profit. A is again if the length of A is less than 2. Just solve and output. So I'll just say that I'll call it the profit L, max L, and the min L is equal to the output of max profit of A, 0 going to n over 2, then the profit R, the max R, and the min of R is the output of the max profit procedure from A of n over 2 plus 1 to n minus 1. Now, we'll say that the new profit is equal to the maximum of the profit from the left, the profit from the right, and the max in the right and the min in the left. Because you already have those values available to you. And max R minus min L. So this is the new profit. But we also have to compute the new max and the new min, because we have to return all three values. But the new max is easy. That's the maximum of max L and max R. And the new minimum is also easy. Is the minimum of min L and min R. And then so you just output the tuple. The new profit, the new max, the new min. Right? Quite clever. Does this make sense? So observe O of 1, T of n over 2 there, T of n over 2 there. That's O of 1, O of 1, O of 1, O of 1. So the combine is also O of 1. So the recurrence that we get in T of 1 is O of 1. Okay? So it's clear? Any questions about that? This is less common as a recurrence, but also appears. Maybe this is like the second most common one. Most common one is the nlog n one. So let's look at this recurrence. So I'll just say this is whatever, this is some constant c. So let's just do the usual. Let's go ahead and draw the tree, the recursion tree. And then let's do the total work. So how much is the work in each node? What is the extra in that node? C. And what is the work in this node? C over 2. Here's the recurrence, right? How much is the combined work over there? Still C. It's different. Previously, the combined work was decreasing as you went down. Now the combined work is actually constant. Okay, now let's do the total. This is at most C. I'll just write the upper bound. What is the upper bound here? 2 times C. Here? 4 times C. What is it going to be in the next level? 8 times C. What is it going to be in the very last level? Sorry?
2 to the n minus 1 times C.
Not 2 to the n minus 1. Why 2 to the n minus 1? How, what? Yeah, log. Log 2 to the log base 2n. What is 2 to the log base 2n? N. N, right? What you get at the end is n times C. So the sum is the summation of I going from, I'll say it's actually, I mean, it doesn't matter, but it's going from 0 to log base 2n of 2 to the I times C. What is that thing? How much is this? 2 times nc at most. Right? What is, okay, so maybe, sorry, let me put this on. Does everyone follow up to this stage? Do you see how the work is increasing exponentially as the levels increase? In the merge sort, it was just equal for each level. Now it's increasing exponentially as you go down the tree. See, another way to think of this is that every node has at most c. How many nodes are there? Well, you have at most, actually, you have O of n nodes. That's the number of recursive calls. So there are many ways of sort of slicing this pizza. But let's do it this way. Okay, so let me move this over here so that you have how much is this summation? Can you give me a precise formula for that sum? What is this thing called? It's a geometric series, right? It's a sum of a geometric series. You need to know the sum for a geometric series. Right? That's why they taught you. They taught you so that one day when you do algorithms, you need to know this. Here, I'll come to my pet peeve about mathematics education. What is the integral of e to the x dx? Or just e to the x. So you remember that?
Yeah.
I'm blaming most of you remember that. It's the same thing, right? What does that mean? It means that when you take the sum of a geometric series, it's increasing by a constant, the last term is essentially everything. The integral of e to the x means that you're summing e to the x all the way up to x, and that sum is just e to the x, it's just the last thing. This is the formula for this of 2 to the I, where I goes from 0 to k, is 2 to the k plus 1 minus 1. Right? In general, when you have I equals 0 to k, alpha to the I, where alpha is greater than 1, then this is alpha to the k plus 1 minus 1 divided by alpha minus 1. Right? And alpha is less than 1, it's flipped. Another way to think of this is you have an exponentially increasing function, and you're summing this up term by term. It increases so rapidly that the last term is essentially everything. Where have you seen something like this? Today. Where do we see exponential growth today? Huh? Yeah? Sorry? COVID, exactly, right? That's why it's exponential increase. If you look at the numbers and you go back and see how many people are infected in the past week, that's actually more. That's like the bulk of the infections that have happened. Maybe now it's coming down, so it's not that bad. But in the middle of Omicron, the number of people who got infected over the past week was more than the number of people who probably got infected in the entire history. Which is why pandemics are so hard, right? Because what happens in the last week is more than what has happened so far. It's the same thing. That's what's happening in exponential growth. In exponential decay, which is when alpha is less than 1, it's the opposite. The first term is the most important one, and everything else just decays rapidly. Anyway, so this thing is actually exactly c times 2 to the log base 2 of n plus 1 minus 1. This is c 2n minus 1. Whatever, this is at most 2cn. Anyway, the upshot of all of this is when you have this recurrence here, you guess that t of n This is like our guess. Then you have to prove this by induction. There's actually a slight challenge in that proof, but okay, I'll just say it out now, that if you try to prove this by induction, you'll get stuck. But what you can prove, what's the best way for me to say this? So, prove that T of n is at most 2c I think this should be correct, but you can prove this by induction. What's kind of weird is if you try to prove 2cn directly, you get stuck, but if you prove 2cn minus 1, then that goes through. You'll see when you do the proof. But anyway, the upshot of this is if you look at this recursion tree, all the work is happening at the last levels, the last level. In Mergesort, equal work is happening at every level. Right? And this is basically, the principle here is exponential growth. And when you have exponential growth, the last terms dominate the series. And when you have exponential decay, it's the other way around. So you'll see in the recurrences, either you get exponential growth or you'll see exponential decay, in which case the work done in the first level is almost everything.